Post-operational cleanout includes a regulated requirement to measure dose rates around nuclear facilities each year, resulting in a trend towards robotic deployment to gain an improved understanding during nuclear decommissioning phases. In this work, we present a novel implementation and real-world deployment of a cyber-physical system comprised of a multi-robot team coordinated by a human-in-the-loop through a digital twin interface. The Symbiotic multi-robot fleet, or SMURF, consisted of the following robots: Agile X Scout 2.0 and Mini, DJI Telodrone, Karma 2 robot, Franca manipulator arm, and a Boston Dynamics Spot with arm. The demonstration of the heterogeneous SMURF included a real-world scenario where UK regulation requires nuclear operators to access and complete characterisation of a site every 3 to 6 months to assess for radiation levels and asset health monitoring. Symbiotic interactions were achieved across the SMURF, where robots utilised automated collaborative governance to work together, where a single robot would face challenges in full characterisation of radiation, thereby leveraging the capability across the multi-robot fleet. In Step A, the goal was to account for dynamic changes in the environment that may not align with the previous building information models. Therefore, a pair of Agile Scout robots equipped with LiDAR mapped the area first. The data gathered was used to create an updated digital twin of the facility as viewed, where results of the 3D mapping task are overlaid with the digital twin of the inspection areas. Step B involved the deployment of a Telo UAV to perform an aerial survey. This was achieved by relaying a live camera feed to the operator and reflecting the results of the inspection to the DT interface. In the mission, we introduced a physical simulation of an oil barrel leaking with an unknown substance. This area required further inspection, where the live feed from the teleoperated drone enabled for the hazard to be further investigated to ensure containment of a potential radioactive material. For this video, we utilise red boxes to highlight the area which exhibits the aqueous contamination. A key aim of a symbiotic partnership includes a robotic fleet which can leverage capability. Whilst the DJI Telodrone is an entry-level aerial vehicle, the drone leverages the capability of the agile ground robots in this scenario, as it can inspect any high or confined spaces with ease. This leads into the first symbiotic interaction to optimise overall mission performance. To minimise issues within autonomy, the nuclear sector currently favours teleoperation over full autonomy for low-level robotic inspections, as in the case of a failure, a human can immediately teleoperate to rectify the mission. It can also be useful to have a secondary robot to provide an overview of a scenario, which can inform on the next steps to rectify any issues. Hazards identified by the human operator are marked within the digital twin around the facility, where in this case, the Karma 2 robot is next deployed to evaluate the area next to the barrel. The objectives of this is to establish if the area is radioactive and if the area is aqueous, as this could lead to further spread of the substance. The Karma 2 robot is an autonomous ground vehicle that was designed specifically for health physics surveying. Firstly, the robot is teleoperated to the area of concern to evaluate the aqueous contamination. This is completed by a non-contact microwave sensor which distinguishes that the area is in fact wet. The robot is also equipped with a Thermo Fisher Scientific DP6 probe for alpha and beta detection, and a Radii G10 dosimeter for measuring gamma radiation. The robot then uses this data to generate a radiation heat map of the environment. These steps are necessary to inform on safe measures to resolve these issues during post-operational cleanout, allowing for more information to be collected about the facility. The deployment of Spot was triggered via the operator at the digital twin to complete a predetermined autonomous mission. Spot autonomously moved from the home position using the fiducials for navigation towards the Franca arm to enable for the robot to be provided with the sufficient tool, the gamma sensor. In this inspection scenario, a symbiotic interaction takes place where Spot is deployed to improve the evaluation made by the Karma robot. Due to the ability from the Spot manipulator arm, an evaluation of gamma across the height of the barrel is conducted to allow for increased information for health physics surveying. This segment of the mission is an area which could be considered as more high risk with respect to the nuclear sector. Therefore, for the purposes of this demonstration, we teleoperated the Spot robot to complete the necessary tasks from the controller. However, in future, we expect this would be done autonomously. Spot grasps the gamma sensor and scans from ground level to approximately 1.2 meters high alongside the barrel. The sensor readings were simulated due to safety restrictions when working with live gamma radiation. To reiterate, in this case, the Karma robot and Spot robot complement each other's strengths and weaknesses throughout the mission to leverage the overall mission capability. For example, the Karma robot is a wheeled robot, therefore does not judder as much as the Spot robot. This makes the Karma robot exceptional at mapping the radiation types on the ground, or what we call the X and Y axes. However, the Karma robot faces challenges in scanning heights, or the Z axis, and in overcoming unstructured terrain. This is where Spot can overcome these issues. We produced a conceptual image of this visualization through the spawning of 3D disk objects, where size and colour can be mapped based on dosage readings. To implement this concept in Unity 3D, we mapped a range of simulated recorded gamma dosage into 10 levels, 1 being the lowest and 10 being the highest, and allocated size and colour parameters for each scan. The discs were then stacked vertically from the lowest height at the ground level to its maximum height, where the sensor readings were simulated for safety purposes. On the right hand side, you can view our symbiotic digital architecture from our system of systems approach. Our key results include the first implementation of a cyber-physical Smurf within the RACO 1 mock-up nuclear facility, implementation of a semi-autonomous mission using a heterogeneous multi-robot fleet in a cyber-physical system, symbiotic interactions where robots can assist each other in missions to improve inspection and adapt to mission challenges, and finally, non-contact detection of aqueous waste that could be radioactive and therefore hazardous. Within our digital twin, we aimed to reduce operator overload as identified as a barrier within the DARPA Subterranean Challenge. We utilised markers to identify areas of interest for the human in the loop. A key benefit of having a Smurf enables for improved overall mission performance. As the mission adapts, so too can the robotic fleet via symbiotic interactions to overcome challenges. A digital twin is a key enabler in ensuring the organisation of a multi-robot fleet and visualisation of what the robotic fleet sees, in addition to circumventing the need for human exposure to dangerous conditions. This symbiotic approach is vital and a necessary step for the optimisation of multi-robot fleets, where regulators encourage a pathway towards a design for symbiotic autonomy. However, we must ensure that the introduction of a multi-robot fleet to a facility does not create an operational hazard. Symbiotic interactions across robots allow for opportunities where robots can be recovered or the safety hazard can be more effectively assessed.